Welcome back to the Gas Compression Podcast. I'm joined for I don't remember how many times you've been on, Jim, but Jim Detorre of FAS Training. He's based out of Colorado, and he's joining us again to talk about some technical and procedural processes in our industry. Jim's business, he goes all over the country, and he trains groups of people to be able to diagnose, to interpret, to really get down into the nitty gritty of what's going on whenever you have a failure. And so he's part detective, part engineer. He's also a great guitar player. And glad to have you back on the show, Jim.
Hey, thanks, Mike. It's good to be here. Good to be back.
All right, so we're going to talk about abrasive wear today, and you got some props there. So for those that are listening, if you want to check out the YouTube version of this, we'll have it up so you can kind of see the things that Jim brought. So abrasive wear. So from a failure analysis standpoint, where do we start with? What do we start with when we're talking about abrasive wear?
Well, Mike, let's start with some numbers. So we diagnose, a handful of failures each year, maybe more than a handful, a couple handfuls, but there's a whole lot more than that going on out there. And 65 to 70% of all the ones that we diagnose are contamination related in one form or another, whether it was through a new assembly that wasn't cleaned properly during assembly, or field work that's been done where the component's been opened up in the field, or maybe it's been remanned and some cleanliness processes weren't followed. But boy, it's just all across the board, man. Yeah, bad air filtration, oil leaks, you name it, contaminated oil. It can all contribute to the abrasive wear related failure.
So when I think of abrasive wear, I'm thinking metal to metal. That's kind of, I don't even really think about contamination. I think about metal to metal. Is that?
So it's a little different than that, Mike. Initially, I'm going to break it down into two types of abrasive wear for you. One of them that we refer to as two-body abrasive wear. That's two-body, and then and that would be what we would consider normal wear in most components. You have a car, the engine's going to wear out, even if your maintenance practices are optimal, right? So we have two-body abrasive wear, which is considered normal wear. It would be kind of like the engine in your car, wearing out at 300,000 miles, even if you had optimal service practices, right? It's eventually going to happen.
Mhm.
Now, when that wear becomes accelerated, we consider that abnormal. But that would be something similar to piston rings riding on a cylinder wall, or a crosshead riding in a guide, or a piston seal and piston wear band riding in a cylinder of a compressor. So when we talk about two bodies, we're talking about the seal or the wear band being one body, and then the cylinder surface being the second body. And what we like to do is we like to put a film of oil between that, a thin film of oil, to be able to help cool, help seal, and help lubricate, right? Keep those surfaces from making that metal to metal contact. Technically speaking, it is metal to metal contact, but it's microscopic. It's so small. The points on a surface are so small. They have a particular term for these points on a surface. They call them asperities. And those are the peaks on a surface, which you're well familiar with machining processes and the different roughness averages that you can attain, whether it's, on various parts, right?
Mhm.
So the rougher the part, the more peaks you have, and the more potential for that metal to metal contact between those peaks, right? When we put the correct finish on surfaces, and then we also have the correct lubrication at the correct temperature, and pressure, then we keep those surfaces separated where they're just making that tiny points where they're just making that small point contact, and they gradually wear over time, and then clearances open up and we start to lose performance, right? And that's when things need to be overhauled. So we refer to that as two-body abrasive wear. And this is a very common thing that happens whenever we start up a compressor or an engine. Is the crankshaft slides across the bearing surface, there's a little bit of residual oil there, but the crankshaft surface finish and those surface asperities between the crankshaft and the bearing surface touch one another at startup because we haven't developed what we refer to as an oil film or a hydrodynamic oil film that kind of floats the crank on a film of oil, right?
Hmm.
So we don't make that metal to metal contact. By the way, that's when the most severe bearing wear typically happens. Normal wear is during cranking, right? So the first body is the crankshaft, the second body is the bearing. So that would be what we would refer to as two-body abrasive wear. Okay. Um, the wear that we tend to see generate the most amount of failures and premature wear out and just kill durability in any component is three-body abrasive wear. And Mike, that's when we take those surfaces, those fairly tight clearances, and we put an abrasive contaminant or the third body between those sliding surfaces or rolling surfaces, and it starts to do a lot of damage very, very quickly. But what is one of the really bad aspects of it is every time it scratches a surface, it generates secondary debris. And if you scratch a metal surface, well, then that debris is very hard, and it's hard on other parts, and it can lead to catastrophic failure. Um, Sometimes we just see it lead to things like leaks and performance issues and stuff like that. So those are the two abrasive wear types that we see and that we talk about, and then they're kind of known throughout the industry. But that's also what we teach. And while we go into this, if you'd like, I can throw up a couple of slides about some fact gathering that we do that's related to abrasive wear and abrasive wear related failures.
Yeah, I'd love to. Am I correct in assuming that when you talk about that third abrasive, you're talking about contaminants in the oil? Would that be?
Well, Mike, that's a great question. So contaminants can come from multiple places, right? The oil eventually washes them off of surfaces into the sump. Sometimes the filter picks some of it out, right? It doesn't catch all of it, definitely not on the first pass.
Mhm.
But it can be from contaminated oil, and I'm going to go into that when we start getting into a couple of those slides. But there's just a list as long as my arm of different contaminants and ways that they can potentially get in. Some of them kind of blow you away. It's just crazy how we can get different contaminants causing abrasive wear like that, and then causing a failure.
Well, yeah, let's look at those slides and we
Okay.
can kind of walk through some of that.
All right. So this is just a snippet of our principles of wear module that we go through in the training class. We include a ton of hands-on stuff like that, um, so people can walk away with a different perspective on abrasive wear and cleanliness. So as we roll through this, it's important for us to be familiar with the component and the materials that are in the component as well. And I'll give you an example. If we have a catastrophic failure in a component, one of the first places that we like to look to determine, was it metallic, is it potentially lube system related, is the filter.
Hold on,
And we'll take that.
let me ask a clarifying question because I'm not in your world. What would you call a catastrophic failure? How do you define
So
that?
a failure period is when the component can no longer perform its design task. Okay. So that means that the unit goes down, it can't work. When it becomes really catastrophic is when things start flying apart.
Yeah.
Connecting rods go through the side of box
In our
and
world, they call it a crash. If a customer calls and says they need a fast turnaround, they had a crash. I guess
you
that's
know
what
you're absolutely right. So I've heard
okay.
crash and I've heard wreck,
Okay. Yeah.
right? So yeah, I hear them both. Yeah, good point. So when we have a crash like that, um, a lot of times an important thing to do is to pull that filter off, to drain the filter, just pour the oil out of it, and then cut the filter open. And it's important that when you cut the filter open that you use a filter cutting type of tool, so we don't contaminate the filter with things like a sawzall or a hacksaw might create, right? Or a die grinder with the whiz wheel on it or the cutoff wheel. So we cut that filter open and we pull a section of the filter media out. We typically have to cut through it with a knife, and we fold that media up. It's kind of like an accordion, right? And you fold that section up and you wrap a rag around it and clamp it in a vise and just squeeze the living daylights out of it as hard as you can, without just with your hands on the vise. And that squeezes all the oil out. And then we open that filter up, and now we can see debris in that filter. So if we had a bearing failure, Mike, and there was oil present, it's going to carry that failure debris throughout the lubrication system, right? It's going to contaminate everything. And with that being said, if I look in that filter and I use one of our microscopes that we use, a little USB or wireless microscope, I look in that filter, I know what I should see is bearing material, right? And maybe a little bit of carbon if some heat was generated between the crankshaft and the bearing. But I should see things like, babbitt is a common term, or aluminum, maybe a little bit of copper, sometimes some steel as well, right? And what I shouldn't see things like paint chips and little pieces of sand, right? Or little grinding sparks that are little blue balls, right? Things like that, and any foreign contaminant in there. When I see that, that's smoke and gun stuff,
Mm-hmm.
right? That hey, that probably did some considerable bearing damage really, really quickly, because it became, again, the third body abrasive, right?
Yeah.
So we we need to be familiar with the materials that are in the system, because sometimes we see those different materials represented in the filter that we squeeze and inspect. So if it's a particular type of material, it may be a certain color, or maybe a certain texture or something like that. One thing we do is try to identify what that is, so we know where to go. Where did the failure actually happen, right? And we use that to lead us. So being familiar with the component and the materials that are in the system are very important. The next thing would be, we would want to gather some facts in regards to temperatures as well. So remember we talked about the two-body abrasive wear, right? That was just like the piston skirt sliding inside of the cylinder wall in the engine, or the rings on that cylinder liner or cylinder wall surface. So when the temperatures get elevated, those clearances get tighter and the oil films get thinner because of the increase in temperature and pressure on them. And when we see that, the two-body abrasive wear can accelerate very, very rapidly. In fact, sometimes to the point where, what you mentioned earlier, Mike, metal-to-metal contact, right? That's adhesive wear. That's what we're going to cover in the next podcast.
Right.
So temperatures, whether cold or hot, excessively hot or excessively cold is what I should say. Temperatures, whether they're excessively hot or excessively cold, we need to know that, because what happens at high temperatures, things grow, oil films get thinner. At very, very low temperatures, like we saw in Texas a few years back, when we had that big cold snap, it really hurt the gas compression industry pretty bad. A lot of units went down, or wouldn't start because of the cold temperatures and not having oil flow. Because of the viscosity of the oil, they're just not used to running in those temperature ranges, right?
Mm-hmm.
So both of those extreme temperatures have a potential of generating accelerated two-body abrasive wear. Okay, so next we want to get some facts in regards to pressures, and obviously, if the unit's it's a crash and you can't run it anymore, can you check pressures? Well, one place we can go is like the ECM on an engine, and do a product status report download, and that gives us codes and temperatures and tells us how hot things got, whether it's a lube system or an oil system. So we gather facts in those areas as well. All right. And then we need some facts in regards to lubricants. And one of the best places for that is the oil analysis. Right. So we have a particular lab that we use, that does just an amazing job for us. We've been working with them for over 25 years. That's Lab 1 in Phoenix. I'll throw them some props there real quick. Jason Cronlin is the guy you want to talk to there. They do a fantastic job. So we gather facts in those areas. And when we talk about lube facts, Mike, quantity is very important. We need to know what the quantity of lubricant was in the component at the time of failure. So this means, are we over full or are we under full? Right? It's kind of like the high temperature or the low temperature, right? So both of those can cause problems. that are lubrication related. But
Let
then we
me
also
let me
do,
ask you a quick question on that.
yeah, go ahead.
Is every engine and compressor system have their own recommended? Is it based on horsepower or is it based on manufacturer in terms of the quantity? How do you know if you have too much or too little oil in the system?
So it's designed into the unit that's going to be placed into service. So if they're running a full duty cycle like in gas compression, then they're going to have a particular sump size
Hmm.
for that horsepower displacement of the engine and the horsepower rating of it. And with compressors, it's, and I have to say this, it's whatever the manufacturer obviously recommends.
Hmm.
But I want to throw this caveat in there is nowadays there are a lot of units out there that have automatic level switches and sensors, and in the gas compression world there's day tanks and sweetening systems that automatically add lube back. But keep in mind that those are all also mechanical components that can experience problems, right?
Hmm.
Not only can we experience failure with the systems that are mechanical, but sometimes a dipstick is used, right? Just like we check oil in our car, and the dipstick can wear out, it can break, it can get lost, it can get spit out, and then it gets replaced. And the reality is that, man, there are just literally hundreds of different part numbers out there for different dipsticks, which
Hmm.
all going to affect the quantity of oil that's in the pan, right? Either too much or too little. So it's important that we also verify that the dipstick is the correct part number if that's the way that we're checking the oil level. Does
No,
that make sense?
it does, but, and I'm gonna ask a dumb question, but does that happen a lot? Like the dipstick that
So
is in a, that's in an engine is actually not the one that's supposed to be in there?
it happens. I'll just put it that
Wow.
way.
Okay.
Some it definitely happens.
Oh,
Sometimes we see
I mean,
failure.
in the heat of the moment, getting called out at 3 in the morning, uh, I know anything can happen.
It does, yeah, it does definitely in this world. So the quality of the oil is very important for us as well. I should say the quality of the lubricant. So I'm not going to make any recommendations or anything. I know what I run in my own stuff, but we've got customers out there that run all sorts of different lubricants and all sorts of different lubricant manufacturers. And I will say this is that the big lubricant manufacturers, they spend millions of dollars every year in research and development of their additive packages, right? And so that's what we see most of the companies run, most of the big companies. But the quality of the oil doesn't just have to do, Mike, with the brand. It also has to do with the cleanliness of the oil and how are we storing that oil, right? What's inside of the day tank? Is there a bunch of rust and scale that's dropping off and getting into that lube oil in the day tank, right? Things like that. So that could potentially cause abrasive wear again. But when we talk about quality, it's the manufacturer of the oil at the time of failure or the time of inspection, has the quality been hurt because it's been run an excessive number of hours, or it's been overheated multiple times, or it has severe nitration or severe oxidation, all things that really affect the quality of the lubricant that's in the pan, right?
Hmm.
So we gather facts there as well. And probably the best way to get good facts in regards to the lubricant is to take an oil sample and have a lab analyze it. Right. So I'm sure you're familiar with oil sampling, or you've heard of it before,
Uh,
probably.
Familiar with it, but we don't do that. So not personally. We
Sure.
know that you do that, but we don't grab oil samples and have it tested.
When we take an oil sample, to start with, it's important that we take the sample while the oil's hot, if at all possible. It's important that the oil be hot. This is what helps keep particles in suspension in the oil that allows us to get a good representation of what the oil's acting like while the unit's running. When we shut the
In terms of hours, how long is that? There's a failure, there's a crash. How much time do you have to get in there and get a good oil sample?
Oh, geez, boy, that's going to be relative to ambient temperature, but I don't
Sure.
know, hour, maybe 2 hours, but regardless, most of the companies that are out there, they take periodic oil samples, so they have a history of it as well. But
Mhm.
anytime that we have a failure or a problem in a component or a system, it's always a great idea to take an oil sample just so you have that information, right? So so first and foremost, it's important that we take the sample the correct way. It has the oil is it's preferred if the oil is hot. We also need to be sure that our sampling equipment is clean so we don't contaminate the sample, which would give us false indications on the report because the lab doesn't know if the dirt got in when you took the sample or when a repair was performed, right? So it's very important that we keep everything clean there. And I'll go into more detail on that when we do a podcast on it on different ways to take samples and how to take them properly. But once we get that sample and we seal the bottle up and we fill out the label, it's always beneficial to put as much data as possible on the label. One of the things that really helps the oil labs is being able to share with them on that label how much makeup oil has been added over time, right? Because the makeup oil tends to dilute things a little bit. So it helps them make a better interpretation of what they're seeing when they test it chemically. So once we
For
get the
somebody
sample,
who doesn't work on engines like I do, what's
sure,
makeup oil? Is that just adding oil to the system?
exactly, yeah.
Yeah.
So like Mike, there's some systems out there or some units that run, and they sweeten the compressor, or they excuse me, they sweeten the engine oil and they pull some of that engine oil off and they lubricate the compressor with it, right? Cylinders, and And if that's happening, then there's a possibility. I mean, talking with some of our customers, some of those, are using 2, 3 gallons, 4 gallons of oil a day. Now, don't quote me on that number. I think that, that was a conversation that I had with one customer, but that means that you're adding, 2 to 4 gallons a day, probably from your day tank to your sump in your engine. So you could do the math relatively easily if the system's working properly, right?
Mhm.
And be able to determine how much makeup oil's been added. And it's not absolutely necessary. It's just really helpful for the oil lab. Something that doesn't get expressed a lot to people that take samples. So once they get the sample, they do various things with it. I will say this: anytime that we take an oil sample, always note the color of the oil and what it smells like. These are two things that get discounted, right? If it smells burnt, guess what? It,
It is.
it is burnt. And that's important that we know that because there's a reason it's burnt, right? And it could be another system that's contributing to it. So once the oil lab gets it, they're going to run various spectrographic tests and LNF or laser net fine tests and check for oxidation and nitration and viscosity levels and particle counts and things like that. They're checking a variety of wear metals that are present in the oil, from potentially normal or abnormal wear that occurred in the unit. They're also they're also flagging levels when they get excessively high based on manufacturers and historical data that they may have, right? Um, they also break down the different chemical additives or additives that are in the oil to let you know if the additive package has been depleted. Oftentimes when we run our oil too long, then we deplete that ad pack and or hurt a portion of the ad pack, and the oil can't do its job properly, and we run into other problems, right? Lubrication related. So that's just a little bit about the oil samples, and we can go into that pretty deep if you want on a oil sample podcast. All right. So when we're looking at wear types, Mike, this applies to all the wear types we'll talk about in this series of podcasts. It's important that we notate the location of the wear, meaning very specifically, like I'm just going to point to this bearing back here, right? So is the bearing or is the wear favoring the center of the bearing? Is the wear all the way across the surface of the bearing? These both tell me different things, right? If it's just favoring one side of the bearing, there's a possibility that I might have an alignment issue or a profile problem on a crankshaft journal or something like that. If they're fine scratches all the way across, then that tells me that I have very small abrasive particles, what we refer to as clearance size particles, the clearance being the gap between the crankshaft and the bearing itself. They're small enough to get in there and scratch all the way across the bearing. And then sometimes we see that we have scratches that just run right down the center of the bearing, Mike, which means that the debris is usually a little bit larger and it can't get out of the oil hole in the crankshaft and get between that tight clearance between the crank and the bearing. So it just scratches the center of the bearing, right? And when we talk about wear location, these things give us some idea, where to go next, where to look, and other things to gather more factual data on. We also want to verify what wear types we're seeing, because the reality is, Michael, is we don't see just one wear type when a component fails. There's a multitude of them, right? So we need to notate what type of wears or what wear, excuse me, we need to notate what wear types we see. And then we need some facts in regards to load. And sometimes, well, the gas compression industry, it's not usually underloaded very often. A lot of stuff, a lot of stuff gets overloaded, right? And
Yeah.
that's just reality. But sometimes the load gets really excessive really quick. Like if we take a slug of liquid or something like that, the load goes sky high, relatively quickly. Or if we have detonation in an engine, the loading on component parts in that engine goes sky high. Again, these are all areas that we can gather more factual data from, right? From like the ECM downloads and things like that.
Mm-hmm.
All right. So the wear types that we talk about in our training classes are abrasive, which is the most common wear type that we see. 65 to 70% of the failures and premature wear outs that we see are related to abrasive types of wear. Adhesive wear is the metal to metal contact that you were talking about earlier, Mike. They're doing this, generating heat when your hands are cold, right? So that's the fastest progressing wear type. And then we go into corrosion. So we're going to cover these three in the series of podcasts: adhesive and corrosion as well. Erosion, or the erosive wear types, tend to be a little bit slower. They deal primarily with particle impact, or cavitation erosion, which is high pressure fluid jet impact on parts. So I'll leave that up to you if you think those would be something that the listeners would be interested in hearing about. We can take a look at that later.
Sure.
But contact stress fatigue is another type of wear that we see, and this can be fast or slow. We see this on various parts that experience sliding loads, such as crossheads or engine bearings as well, or compressor bearings, right? Then we have fretting, and we're going to do on in the series on fretting and fretting corrosion, and that can be fast or slow because we tend to see a lot of that industry wide, and a lot of guys aren't really familiar with it and how critical it is to understand it and address it at repair or rebuild time. So those are the wear types that we cover. So I was going to start with the 2-body and 3-body. So how are we looking for time?
Oh, we're good.
Okay. All right. So I was going to start with the 2-body and 3-body wear types. So the 2-body wear type we discussed earlier on when we have a metal surface that has peaks or valleys on a surface. So we talked about 2-body and 3-body abrasive wear types a little bit earlier in the podcast. So when we talk about 2-body abrasive wear, that would be these peaks here touching these peaks here. So it's just a very microscopic contact point when those parts are either sliding or rolling against one another. And we have a lubricant film there. So we're not generating any heat. And this becomes what we call normal wear. That's the 2-body abrasive wear. The 3-body abrasive wear is when we put this dude here in the middle, right? And that thing, it's sliding, it's gouging, it's rolling. I like this term. It's plowing, or it's
Mm-hmm.
tumbling. What happens when you plow? Well, when you plow through the earth, you raise spoil pile on either side, right? That's what happens when a hard particle plows through a bearing like that.
Mm-hmm.
And then as it raises up that material, like the sides of the ditch, then these surfaces here make contact easier, and a lot larger surface making contact. So then the metal to metal contact really accelerates considerably. So the 2-body and 3-body abrasive wear, 2-body, one part's coming in contact with another part, usually in a sliding or rolling operation. We consider this normal wear unless it's really accelerated. And what I mean by accelerated, Mike, I just wrote an article, What Went Wrong in Gas Compression Magazine. And I think that's going to be out in the January issue. But there's a good one in there about surface asperities and 2-body abrasive wear and accelerated 2-body abrasive wear on a 15-minute run-in of an aerial recip compressor. It ended up smoking a bearing or wiping a bearing, right? But
Wow.
the other bearing showed that accelerated 2-body abrasive wear, which we shouldn't. We should see that over a long period of time rather than 15 minutes, right? All right. So when we put this dude in here, that creates just a whole nother host of issues. The big thing is not only is it raising up material and potentially causing metal to metal contact, but as you can see back here, it's digging material out and it's generating secondary debris. And then that secondary debris does the same thing, Mike, and it generates secondary debris or adhesive wear. And as this accelerates, things wear out really, really fast,
Mm-hmm.
right? And potentially fail. So here's an example here. These are some bearings that were out of an engine, and you can see that the scratches are all the way across the surface of the bearing, right? So just for reference here, so these are upper bearings, Mike, in
Mm-hmm.
an engine. So they've got an oil groove down the center of them, and off the screen there, I can't see it on my screen, but there would be an oil hole there. So when you see the scratches all the way across that surface and all the way across this surface, again, that tells us something about the clearance sized particles, the small pieces of machining chip. You can see we're magnified about 100 power here. And this is a little piece of cast iron, and it's curved and it's got some cut lines in it, like a little, machining tool that took a burr off somewhere or machined something somewhere in an oil gallery in the block when it went out to the machine shop, not dinging the machine shop, because like we tell our guys in class, who's responsible for cleanliness when you put the component together, the machine shop or the assembler? It's
That's right.
always the assembler. Right.
I'm gonna put
So
that. I'm gonna put that on all of our work that we send out of our shop. That you said that.
that's fine. Yeah. I'm a firm believer in it. Yeah. Unless you've promised them that they're ready to install, right?
Right.
And yeah, okay. So this piece of debris here is what's encircled in this red square here. And we're looking at it at about 100 power. So it's a little piece of machining chip, cast iron material. It's to it. It's very rectangular, and and as those pieces are going through, they're also breaking apart and making other pieces that are doing damage bearing here, cause all the abrasive scratching we see. This from crankshafts not being cleaned properly after somebody has hand polished them, and abrasive contaminants and metal have gone to the oil holes. And then when they first run the unit, it gets pushed out right into the bearing. Right. So we see several different types of problems like this. You can tell they're pretty much brand new, right?
Mm-hmm. Yeah.
So these clearance size particles right down the center. Yeah, right down the center, and that main wear track width is about the same diameter as the oil hole in the crankshaft. So what this indicates to us, Mike, is these particles here uh, are larger in nature. So what we've got on the right here is this piece of cast iron, what appears to be cast iron machining chip. It's got some curvature to it. It had some lines in it that we could see with the microscope. It's rectangular in shape, and it's breaking apart, and it's scratching this bearing all the way across here. And it's not the only one, guaranteed. There are others in there as well. Some of them are embedding, like in this area here. But here you can see that's the same area that's encircled in red here. We're about 100 power magnification to be able to see how big that piece of material is. So, and that one there, keep in mind that that's just embedded, stuck right in that oil groove, Mike.
Mm-hmm.
So it's not a clearance sized particle, right?
Mm-hmm.
It's embedding right there, but the smaller pieces are the ones that are going in and scratching these surfaces here. So when we look at this bearing here, the primary scratches are right down the center of the bearing, and they're also the same width of the oil hole of the crankshaft. So what this tells me is these particles are larger in nature. They're not clearance sized. They can't get between the surfaces and do the damage that we saw on the previous slide or the previous bearing. So they're going to continue to gouge these areas out, and the debris that it's digging out of here, oil flow is constantly flowing outwards. So that debris is getting embedded by the crankshaft in this area here. So most of what you're seeing here is the debris that's been dug out. Some of it looks very black, right?
Hmm.
And it's not. It's actually highly polished, and it's reflecting my black shirt that I was wearing when I took the picture.
Huh.
Yeah, it's crazy the way that things look, right, when we photograph them. So that tells us a little bit about clearance size particles and non-clearance size particles, right?
Hmm.
And oftentimes the larger pieces tend to not do necessarily as much damage um, over long periods of time, right? Where the smaller particles, those are the things that are wearing components out.
So
And
what would lead to this type of abrasive wear? What would be a cause of this?
oh geez, so here we go. um it could be as simple as a jug of it hasn't had a cap on it for a month and a rag's been stuck in it, and you pour some of that oil in the component and it's got dirt and water and all sorts of stuff like that. That's one way that we could cause this to happen. Another way would be is that we take a cylinder head off and we don't clean the top of the engine and the outside of the engine before we disassemble it. So as you're disassembling it, debris is going in. And
Hmm.
then if we're not careful in cleaning processes, such as using like gasket scrapers or die grinders with roll-lock discs or Scotch Brite pads, we need to think about when we clean, where's that stuff going? You know, is it going right into the sump? We need to try to do everything that we can to keep those areas just as clean as possible. Something else, most of the guys do a great job. There's no question about it. It's pretty rare that when I go out and I see somebody doing an overhaul, that if they're working on, one cylinder at a time, which is the case, and, in most cases, all the others are completely uncovered. Nothing's covered up. So now we run into airborne debris, right? And you ask what could cause these problems. Well, the airborne debris is a whole nother host of issues,
Hmm.
especially especially kind of in the dust belt, right? When we start getting into certain parts of Oklahoma where the wind's blowing and the dust is so bad, it's just really challenging to keep things clean. And I understand that. I was in a service truck for a long time working on equipment, and I did my due diligence. I learned about these things early on in my career, and cleanliness is very, very important, especially when it comes to durability and longevity of the component, right? Not just not just failure wise, but when it comes time to rebuild a component, if you're having an exorbitant cost because you're having to replace so many parts, sometimes that's something that starts to raise some questions, some maintenance questions, things like that. So there are multiple places that the debris can come from, Mike. One of them that we talk about in our classes is a dead blow hammer, the leaking dead blow hammer. So are you familiar with what a dead blow hammer is?
Oh yeah, we call them chop hammers, but yeah, dead blow hammer.
Yeah. So you see the one that the face on it's kind of flapping, right? And the canister inside's all dinged and dented up, and it's been leaking little BBs into the component every time you use it. I I was doing some QC on an engine overhaul a few years back, and I walked in, I saw a hammer just like that, and guys were doing their toolbox meeting, and the guy looks over at me, he's like, I was gonna replace that. Probably after the overhaul, right?
Uh-huh.
But that's another place we see just crazy stuff. Like an engine that had been disassembled in the field and covered up with tarps and sat for a couple of days, and some mud daubers or mud wasps got up inside of it and made their nest, and that ended up causing issues, right? It caused a bearing failure on an overhauled engine.
I
And let
guess
me tell you,
everything can be traced back to cleanliness.
a lot can, a whole
Yeah.
lot can. That's probably the biggest win, right? Is keeping things clean. But this one was crazy. Remember we talked earlier, Mike, about looking at the filter with the microscope, right?
Hmm.
And when you look at the filter and you see a little bug larva looking back at you. Yeah, got
That's a
pictures of them,
problem.
man. Yeah, it's crazy, but definitely. So there's just so many areas. I have to mention a good friend of mine. He owns a high performance engine rebuild shop in Jackson, Mississippi. His name's Jeff Burrows. I want to give Jeff a shout out. Um, Jeff builds some really nice stuff, a really nice product. He's a full service engine machine shop, but he ended up growing up working in that shop with his dad. And he tells me the story when we have the cleanliness conversation. He says, Jimmy, my daddy, when I was growing up, he said, if it wasn't clean enough to go in your mouth, son, it wasn't clean enough to go in that engine. And, I kind of that's that's the way to be, right?
Yeah.
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 So I hear a lot of people say, oh man, our equipment's big and it's tough and it can handle a lot of that. And I totally agree. It can, but when it does fail, people want answers,
That's
right?
right.
When it wears out prematurely, people want answers. Um, Sometimes we're just throwing a lot of money at it. Sometimes we're having to throw extra resources that we don't have, especially with the lack of technicians out there. If you've got a guy working on something because it was put together dirty 6 months ago when he should be out maintaining the rest of your fleet, and when that
Hmm.
one it was just overhauled 6 months ago, so it should run for a couple of years without any major stuff, right?
Hmm.
So all right. So here you go. This is a filter element up on the upper right quadrant that we're looking at. And I'm looking at this at about 70 power with the microscope, Mike. And this is the filter media that you see, right? And this is the bearing material, the aluminum and the steel and a little bit of carbon. And can you see these little rocks here?
Hmm.
So those are
Wow.
sand particles. And then I also took a sample down in this lower left quadrant off of the debris that was on the floor in the shop that this engine was overhauled on. Now this is a big expensive engine, and it failed on the dyno test. Right, so it had to come completely back apart and have another crankshaft put in it and a whole new set of bearings. Right,
Wow.
this stuff gets expensive really fast, and just a whole host of other issues that come along with it. But you can see these pieces of sand here, right?
Hmm.
Real similar to what we see there. And this is just what was on the floor. So that tells me that it becomes airborne. Anything that's on your floor when you're assembling something, whether a forklift drives through, a guy walks by, whatever, it becomes airborne, right? Can you see this little blue spherical thing here, Mike?
Hmm.
That's what a grinding spark looks like at about 70 power under the microscope.
Wow.
Yeah, it's crazy, huh? Yeah. So so this was a fresh overhaul. This here had about 350 hours on it, and this particular engine, um, I believe this was a Caterpillar 3500 engine, and during the overhaul, it was a major in-frame overhaul, and they didn't, because of accessibility or whatever reason, or it got forgotten about, they didn't pull the suction screen for the oil pump that mounts to the end of the oil pan, and they had a catastrophic bearing failure just a few hundred hours after overhaul. And this was some of the stuff I pulled out of the screen.
Are those
So
paint
this
chips?
so this is paint here. I'm in the lower right quadrant here now, Mike.
Yeah.
Right, you see the scale here. We can tell the size of these pieces. These are pretty good sized pieces, right? I mean, that's an inch right
Yeah.
there, right? So this stuff here is gasket material. This black stuff up here is O-ring material. This is a paint chip. This fibrous stuff here are pig mat fibers, which is like an oil absorbent mat,
Hmm. Hmm.
right? And then once we got the big stuff out of the screen, we move up into the upper left quadrant and we see the smaller stuff. And yeah, there's like 5 different colors of paint represented there. Right.
Wow.
So always important to clean things before we take them apart, right? And to try to keep them as clean as we can when we go back together with them.
Wow.
Yeah. So anyway, a little bit more here about wear location, right? We're taking a look at it. This is a piston here. Um, the natural gas guys will give me a hard time because this is a diesel piston. I'll say, yeah, the dirty diesel guy, right? But that's okay. We work on all of it. But this is my top compression ring, and this engine had been sucking dirt, Mike, for about 800 hours, and it sucking the dirt wiped out that top ring. So now all of my combustion gases are getting past that ring, and this one's having to do the job of sealing it. So this is no longer doing its job, and I'm getting a lot of carbon buildup and residue buildup in this area here, right?
Mm-hmm.
Just because what they call a bellows or a boot, and it's basically a boot that joins two pipes together with hose clamps on it that the air can flow through, and one of those clamps got left off. So it was sucking dirt and wiping out the top ring and wiping out the cylinder walls, right? So this is another way that abrasive wear can have a negative impact on things. So when we talk about what are possible contaminants in lubricants, this is a good one, and I kind of wish I'd have put a list together that we could put on the screen that people could see, but I guess they could write them down, But when we talk about contaminants and lubricants, it's the tell-all answer is, what's a contaminant in a lubricant? Anything that doesn't belong.
Yeah.
So what doesn't belong are the grinding sparks, or the very small rocks, or the sand, or the dirt, or the paint chips, or the abrasive media from cleaning tools, or things like excessive amounts of assembly lube or greases when we put something together. Things like that, excessive amounts of sealants, anaerobic or RTV sealants. When we squeeze those between a surface, if we put too much, it squeezes out, but it also squeezes in. And then with the hot oil flushing over it over time, it loses its resiliency and the pieces break off and they get sucked right through the suction screen and get into the filter and get into the bearings, things like that. So dirt, bugs, grass, sticks, blasting media. There's just a whole host of different blast medias, from walnut shells to baking powder to melamine to glass beads. We see all of that stuff. The pig mat fibers,
Mm-hmm.
um, oil absorbent mat, the kitty litter. The folks that still use kitty litter in their shops to clean up oil, that stuff it becomes airbound or airborne. Excuse me. Folks that use kitty litter in their shops, when you're sweeping that up, it becomes airborne immediately. When we walk into a shop, and sometimes there's that guy, and look, if you're that guy, I'm not picking on you, but don't use the air nozzle to blow out your bay, especially when you've got components on the bench, because that big dust cloud that you just created, it's covering everything.
Mm-hmm.
So keeping things again as clean as possible. Cloth rag fibers are something that, the preferred method of wiping, or a type of wiping device, is kind of like a wipe all towel. They come in a box, they're lint free, they don't generate secondary debris,
Mm-hmm.
things like that. So and then we've got the contaminants that are just generated inside of the component as the process of combustion, Mike, right? Or as a process of compression and gas flowing through the compressor, whether they're salts or sands, or abrasive bits that cause all sorts of types of damage that we see in the form of abrasive wear. So
Mm-hmm.
the list gets pretty long, doesn't it?
It does. My gosh.
Yeah. So you can see that the list is pretty long when it comes to potential contaminants and lubricants, right?
Yeah.
That's pretty much it for the principles of wear when it comes to abrasive wear types for today, Michael. So
Yeah.
I
So
think
just to recap a few things here. Again, I think what I've heard you say over and over and over and over is cleanliness. It all starts with cleanliness, right?
I believe so. Yes, sir.
Yeah. All right. So to recap, what are some quick tips and things that the mechanics and field techs out there need to be doing or not doing?
So I think one thing that we can start with is always be cognizant of your environment. If there's a lot of blowing dust, that's not the optimal time to open a component up. If you have to, you need to try to keep it covered up as much and as quickly as possible. But also, always start with cleaning it off first. Clean as many surfaces as you can. A couple of tools to have with you, a long air nozzle. A 2 or 3 foot long air nozzle works pretty good for blowing a lot of stuff off. I know I said don't blow out the bay earlier, but we're talking about field repairs out in the field, right?
Right.
Also, on my truck, I had a really small, it wasn't very big around, just a little shop vac, right? So I could get in areas with a screwdriver or a bar and dig out the crusties and kind of vacuum everything up. And if stuff did drop down inside the engine, I had it right there. I could just suck it out pretty quick. Um, that's pretty helpful, but then you need electricity or a generator running, to be able to power that. I highly recommend that if you take something apart, cover it up as quickly as possible. If you take hoses loose or you take tubes loose or any tubing, air piping, anything like that, cover the ends as quick as possible to help prevent the contamination from getting in there. Some guys are under the school of thought that, well, I've got to clean it anyway. Well, the less opportunity you have for debris getting in there means that even after you clean it, the less opportunity for debris still being in there, right? So those are just a few things that I think would be pretty helpful. Keeping things covered up. A couple things that work really well is the paper blankets. The paper blankets, you get those from just about anywhere, Granger or anywhere, and some magnets. Man, those work the world, right? So you got a handful of magnets, you lay that paper cloth on there, drop the magnets on top of it, and then just start moving your magnets and peeling your cloth back as you go down the line, doing cylinder after cylinder. It's going to keep a lot of debris out.
Yeah.
So just
That's
some
a,
little tips.
yeah.
Some guys will say, I don't have time to do that and all that. Well, thank you for the potential work in the future when the failure happens. We get the opportunity to analyze it. So I hope it doesn't happen to anybody, but it does happen, right?
Right. Try to save a few minutes and you might actually cost several tens of thousands of dollars.
Oh, we've seen it. Yeah. Yeah, or hundreds of thousands of dollars. When you're talking replacing a 3616 crankshaft because something was dirty going together,
Oh.
whew, gets pretty pricey pretty quick.
Well, Jim, thanks again for coming on. And you are uh, you are the expert here, and I want to make sure everyone understands what you do and what your business does is hosting these classes for companies to send their field techs and mechanics to come in and get a really deep dive into all of this. And so I know you're booked up, but when is your next opening for your next class?
So, Michael, it's looking like we'll have an open enrollment class the week after the EGCR. The EGCR Eastern Gas Compression Roundtable Conference is May 7th through 9th. I will be teaching a class there. It'll probably be just an hour or two class. And then we have an open enrollment class planned from May 13th, ending on May 16th in Cannonsburg, Pennsylvania, which is just right down the street from the EGCR as well.
Okay.
So that's our next upcoming open enrollment. Hope to see some folks in there. So
So if people wanted to get on a list in case there's a cancellation, how do they get a hold of you? How do they register?
go to www.fas-training.com.
Okay.
And there'll be a link there that'll pop up and you just put your information in and we'll get right back in touch with you.
Awesome. Well, I'm looking forward to doing the next set of series. I think you have a lot of value that you bring to the community and in the industry as a whole. So thanks for what you're doing and looking forward to doing a few more of these.
Well, thanks, Michael. It's always a pleasure.
See you soon.
All right, buddy.